So I think, yeah, maybe I can share my slides first, right? Is it okay?
For a moment. No, please. I already opened.
Okay. Yep.
All right.
But generally, the first assignment on the questions, right? They are quite well done by the students, right? So I can see quite a number of people answering most of the questions correctly, right? So it is quite good lah, right? Quite happy lah to see this, right? Yeah. So we have about 13 people, right? Okay.
Around maybe
I think 14.
Maybe five students will join, and also some participants from the graduate program also join with us. We have Pak Febri here. Very good morning, Pak Febri. Thank you for joining.
Okay.
Yeah. I guess we can start. Yeah.
Okay.
To keep the time to be on time. So please, Dr. Wenda, let me show.
Okay, so thank you for your invitation to give this lecture. So today we want to go through certain things like transport and also to some extent abiotic reaction in the environment. So just to go through what we have gone through over the past few weeks, we have gone through some introduction, dose-response relationship, and then toxicodynamics and toxicokinetics, which is basically more towards biological system, right? We talk about how the toxicant can actually affect humans and what kind of effects that the toxicant can bring. Then after that, we look into the mode of toxic action. This one is more related to the chemical part, okay, the chemistry of the pollutant or the toxicant and how they are in the environment. So today we want to continue a bit from last week's. We left out on the transport, right? So this week we are going to cover on the transport, okay, and the fate of the pollutant in the environment. And then we also want to look into the abiotic reaction. So looking at the slides, I think I will start off with the abiotic reaction in the environment. Okay, after that, I will look into the transport. Okay, so there will be two parts in today's lecture. One is the abiotic reaction, okay, and then the other one will be the transport and the fate. So we are going to look at the processes that governs this transport of the pollutants, and then what kind of reaction that these pollutants can undergo in the environment. A very simple outline of what we are going to cover, which is to describe the possible mode of transport, to understand the major abiotic chemical reaction, and usually in the environment, the major pathway involve these photochemical reactions. So we are going to look into it. And finally, we want to look into the description of electrophilic, nucleophilic, hydrolysis, and redox reaction. So these are the reactions that can occur in the environment, right? So let's start off with the abiotic reaction in the environment. So one of the most important reaction, right, in the environment would be the photochemical reaction. So if you look at the name itself, right, photo and chemical, right, you can roughly guess that this photochemical reaction means that this photo would be the light, right, the light from the sun. Okay, most of the time it's from the sun, which can induce certain chemical reaction in the environment. So that means we are actually looking into how the sun, as a major source of energy, can create certain opportunity for reaction to happen, right? So usually in this kind of process, the photochemical reaction involve endothermic process, because as you know, the sun provides energy, and then this energy is absorbed by certain pollutant in the environment, okay? And the absorption of this energy enables the reaction to happen, right? So if absorption of energy, usually we call it as endothermic process. This one you can learn it in the physical chemistry, endothermic reaction, right? So the energy comes from the sun. It comes from the photons. Photons here means that it is the radiation, okay, light radiation. we call it as photons, right? It has a lot of energy that can actually excite the molecules to a point whereby it can react with many things. So UV visible energy is one of the strongest energy. If you look at many people like to go to the beach, right? They like to walk around in the beach without wearing anything. So usually when we go to the beach, right, it is quite exposed. It has a lot of radiation, the sun radiation. If you walk around without any sunscreen, you will see that the next day when you wake up, your body will turn into reddish color. Right, your skin may be peeled off, and you will suffer from something called a sunburn. So sunburn comes from the UV radiation from the sun. So this UV radiation is strong enough to cause our skin to have issues, right? So it is also strong enough to provide energy to break some of the chemical bonds that you find in organic molecules, right? So there are many kind of different energy classification in this solar light. One, we have this visible light classification. The other one is the UV light. Okay, these two are the classification of the solar. Aside from this UV and visible light, we also have some infrared in the sunlight, right? So these are the region whereby we have this energy from the sun. Ultraviolet, we have infrared, and to some extent a small portion of it is what we call as visible, right? So basically all these are just classification. Okay, we classify them based on the wavelength, right, of the radiation. So we have like a very long wavelength like radio wave, then we have a shorter wavelength like gamma rays. So if you look at the elementary physics, right, you'll see that there's a relationship between the wavelength and the energy. The shorter the wavelength, the higher the energy, right? So UV is of higher energy over here, right? And then we have visible, not as powerful as UV. Usually this visible is considered as safe for us, right? It's less energetic, right? The one that we are concerned with is the ultraviolet, right? And then the UV itself is the one that is most of the time responsible for inducing chemical reaction. Okay, whereas visible, on the other hand, is less powerful. Okay, it cannot really induce significant chemical reaction. And then we have the IR region. Okay, this part usually can only excite the molecule and cause it to have vibration, right? So it is like not powerful enough to cause excitation of the electron, okay, from the ground state to the excited state. So the area of concern in environment, right, will be the UV and the visible. So usually for an absorption of the radiation to happen, right, we must have a source. Okay, that will be our sun. And then once the sun shines its radiation to a specific molecule, right, this molecule must have something, okay, a functional groups, or what we call as a chromophores, to be able to absorb the photons, right? So after absorption, okay, once the photon has been absorbed by the organic molecules, right, then we have excitation, right? This is something that we call as excitation of the electron. Okay? So the electron can actually move from one state to another state. But this is more of a physical chemistry, right? So, but this is what is happening in the environment. So photon absorption by the organic molecule usually is what we call as the quantized phenomenon, whereby it actually consists of discrete energy levels. So in other words, let's say you have a molecule, right? You cannot just simply irradiate it with any kind of radiation, right? It has to be discrete, it has to be a specific, okay, then there's a specific wavelength whereby you can excite the electron. Okay, this is related to quantum chemistry, right? So the excitation can happen, and then through this excitation, the molecules becomes more reactive, and then the reactivity will cause it to undergo reaction in the environment. right? So this is the basis of photochemistry, right? We are looking into how we can actually use the light to induce certain excitation of the electron in the molecules, and then this molecule can participate in chemical reaction, right? So IR absorption, of course, correspond to vibration excitation. Okay, when we look into infrared absorption, it can cause vibration only because the energy is only enough to cause vibrational excitation. So if we look at UV absorption, okay, on the other hand, we can see that it can actually cause electronic excitation. Okay, that electron itself can move from one lower energy level to higher energy level, right? So UV absorption cause electronic excitation, and usually we can actually classify it, for example, N to pi star. Okay, this is what we call as the movement of electron, okay, excitation of electron from the lone pair to the anti-bonding of the pi orbital, right? And then we have conjugation, which means that the bonding pi orbital is excited to the anti-bonding pi orbital, right? So these are all the basics of the absorption of energy. This is what will happen when you have absorption. Right. So once you have a molecule being excited, right, it can undergo reaction, right? As I mentioned, there will be certain reaction that can occur depending on the type of molecules that you have. So if you have, let's say, a molecules that can undergo a unimolecular reaction, then you have unimolecular reaction, right? So one example of this unimolecular reaction is, for example, direct photolysis. Okay, so this unimolecular reaction means that you have one molecule being decomposed, right? It is split. It can be dissociation. It can be bond breaking. It can be inter-system crossing, right? Example would be this methane. Okay, so this methane, this is a very common environmental chemical. This methane gas can be produced by bacteria, okay, under anaerobic condition, right? In lakes, in rivers, in any places whereby you have the lacking of oxygen, right? So the methane gas itself, when you have it been exposed to this radiation, okay, this is actually H mu, right? So this is what we call as a radiation energy, okay, with a wavelength, let's say 140 nanometers, right? This is under UV region. So when you have these two components come together, you will see that this methane gas will be split into CH2 and hydrogen. Okay, so this is quite interesting because we are actually breaking the bonds, right? We break the bonds and then we produce two different things. This is an example of dissociation. But of course, the percentage of methane being dissociated to this CH2 and hydrogen depends on what we call as the reaction quantum yield. Okay. The other one reaction that can happen is the bimolecular reaction. Okay, bimolecular means that you have two different molecules, okay, combined together. And this is one of the things that can happen when you have excited molecules. An example would be this mercury, right? Mercury sensitization, whereby you have this initially this mercury, right? You can see this is 1s0. This one refers to the electrons, right? This is electrons in the s orbital. When this mercury is excited, right? You add in certain radiation at 253 nanometer. This is under UV also, right? Then you'll see that the electron can be promoted, right? And then you have this excited mercury, right? So the excited mercury can react with this molecule, again, this methane, and then the excited mercury can go back to its original state, right? And then on the other hand, the methane itself will get dissociated. Okay? It will decompose into CH3 and H, right? So this is just a typical example of bimolecular reaction, right? Just to show you what is the significance of the reaction, photochemical reaction, right, in the environment. Okay, so you can see that this is a general way whereby mercury can actually react, and light actually participated in many kinds of reaction for mercury, right? So you can see here, if the light shines on this mercury, right, at the in the sea, okay, in the sea or in the river or maybe in the lake, right, you see that photooxidation can happen. Okay, so you can see here the term photo here means that it is it needs light, okay, light energy like UV or visible radiation. Okay? Most of the time it's UV. So the sunlight can actually cause photooxidation of mercury 0 to become mercury 2 plus, right? Whereas this mercury 2 plus can actually become back to mercury 0 through photoreduction, okay? Also requiring light, okay, UVBs. And mercury 2 plus can undergo photometallation, okay, to become a very, very harmful product, methyl mercury, right? So this methyl mercury can undergo bioaccumulation in animals, in fish, in maybe in humans, okay, and even in sea plants, right? You can have photodemethylation back to the mercury 2 plus. So you can see most of this reaction comes with a photo in front, right? So in terms of breaking the bonds, we need to look at the bond energy, right? So in the environment, right, we have many kinds of organic chemicals, and each of these different kind of organic chemicals, they have different bond energy, right? Some have like, let's say OH bond, right? The bond energy for this is about 465. Okay? So if you calculate, okay, you calculate the wavelength of this 465, you'll see that the light energy is actually in this 257 nanometer, right? And then on the other hand, HH, okay, bond, you need 436. Okay, you calculate, it becomes 274. Same thing for this CH, CO, CC. Okay, you will see that it is between 348 and 415. So the energy, okay, of the bond depends on the stability of that compound and the type of bonding that you have, right? So all these, they are covalent bond, just that different species, right, it will bond differently, right? So the weakest one will be this CCl bond, right, which needs only 243 kilojoule per mole to break, right? So light energy corresponding to this CCl bond will be 492 nanometer. So the higher the energy that you have, right, like for example 465, the lower the wavelength, right? So this is the inverse relationship, right? So just to show you this diagram, this is a typical Jablonski diagram that is often seen in physical chemistry. So this is very relevant to photochemical system. Okay, all those photochemical reaction. Most of the time, if you read about that, you will see this kind of diagram. Okay, this is a diagram that can be used to represent electrons, right, at different states. Right, this is more towards physical chemistry, right? So just to give you some overview of this, this part represents the ground state of electron, whereas this part represents the excited state, right? So when a molecule which has a lot of electrons is being radiated with UV or visible light, so this electron, usually it resides in this ground state, will actually be promoted, okay, promoted from a lower state to a higher energy state. So let's say you have electron over here, right? When you have far infrared radiation, right, you have this molecule being exposed to a far infrared region of the radiation, you'll see that it will undergo this A transition. Okay, the electron will move up, slightly up, higher in terms of its energy level, right? So for it to move up to this, right, it can actually cause rotational transition. Okay, it can rotate. If you have high energy, for example B, right, B here, it goes to B. When it's exposed to near infrared, you will see the electron move to this energy level, right? Then you start to see that it is actually going to vibrate. Okay, it vibrates and then it releases back the infrared energy. Right? So this rotational and vibrational is very less likely to cause any chemical reaction. Okay, it is the UV, okay, UV excitation that will most of the time cause reaction to happen. So UV excitation means that let's say electron is in here, the ground state. Okay, all this white color one is ground state. It's exposed to UV, then this electron move to this level, okay, higher energy level, okay, significantly higher, and this is what we call as the excited state of the electron. Okay, so at the excited state, the energy of the electron is much more higher to cause reaction to happen, and then it can participate in many different kind of reaction, right? Just to show you how this excited state electron can participate. One example would be the intermolecular energy transfer, whereby there are two molecules here, molecule 1 and molecule 2, right? So molecule 1 consists of let's say electron at this ground state. Once you have energy going to this electron goes to the excited state over here, right? So this is presented by M1 star, and this is excited state. And then after that, it can transfer energy to molecule 2. Okay, it depends on whether it is a allowed transition or forbidden transition. So this is more on quantum chemistry, right? So usually, if it's the second molecule has a lower energy level, okay, in its excited state, then of course the electron can actually move from one to another, right? So this is just to show you that these kind of things can happen fundamentally in terms of how energy is absorbed by an organic molecule, right? So once you have this excited organic molecules, so the next thing to ask will be what will happen, right? So the excited electrons in the molecules will cause the molecule to undergo several things. First will be the physical processes. Okay, physical processes will mean that the molecule remains unchanged. So physical processes usually occurs when you have irradiation with those less energy intensive radiation. For example, infrared. Okay, so if you have exposure to infrared, your molecule will vibrate. Okay, so it will vibrate to lose all those energy that it absorbs. And when doing so, you will see that heat will be transferred. Right, so that's why you see most of the time when you have infrared being irradiated on something, then it becomes hot. It's heat because there's a heat transfer due to vibration. Right, so you can also have energy loss by light emission. Okay, this is what we call as a luminescent. For instance, I don't know whether you have seen these things when you bought from the supermarket. It's green color, right? So when you go to the dark room, it glows in the dark. Right. So this is a typical example of energy loss by light emission. Right. So this green color things, right? I don't know what it's called. It's greenish in color. Right. So if you bring it to the dark room, right, it starts to emit light to a certain point whereby there's no more light emitted. So you have to take that things and put it under the UV irradiation to charge that thing, right? So that it can starts to emit energy again. So you bring it to the dark again, and then it starts to glow, right? Glow in greenish color. So this is a typical example of a luminescent. Okay. The other one will be energy transfer by promoting an electron in another chemical species, which is something that we call as photosensitization, which means we are actually sensitizing another chemicals using one chemical. Okay. But then the original molecules remains unchanged, right? So this is also part of the physical processes. So if you have been exposed, okay, you have the organic molecule being exposed to high energy, then we have chemical reactions. Okay, so a chemical reaction can happen in many ways. For example, fragmentation, right, which means your chemical been cleavage, okay, being cleaved to become two or more chemicals. Right. So you have intramolecular rearrangement, which means that your molecule itself can actually rearrange itself through a specific configuration under the exposure of light. Okay. Then we have isomerization, which means an interchange between the cis and trans structure of that particular isomer. Then we have hydrogen removal and electron transfer. Just to have some visual look on what is actually happening. Okay, so let's say you have isomerization, right? So this is what actually happens, right? You have the exposure of these molecules to a specific wavelength of light, and then you can see that it can actually interchange between the cis and the trans form. Okay, so this is one of the good example whereby we can actually see how the light can participate in converting a product into something else. Okay, so if you have less energy, of course you have vibrational motion, rotational motion, and translational motion. So these are the basic movement of the molecules that can happen once you have it being exposed to low energy radiation. Right? On the other hand, this one, okay, this part over here, okay, you can see that this is a classical representation of the electron of an atom, right? So as you know, the electron is not represented like this, like in a round shape. It is actually represented by its orbital. You have s orbital, you have p orbital, you have d orbital, you have s orbital, right? So this is just to show you like how a molecule can actually absorb energy and release it back, right? So you have hydrogen, right, with the electron over here. Then once this electron have certain energy been hitting it, then you can see that it is actually becoming excited. Okay, the color changes, and then the excited electron has to do something to release its energy and go back to the ground state. So what it did was it releases some energy back. Okay, this energy that it released must be lower than the energy that it absorbed. Okay, this is one of the rules in quantum mechanics, right? And also the thermodynamics, right? So the energy that it absorbed, let's say this is UV, right? It is very excited. Then after that, it releases back the energy in the form of a lower energy level. And then it goes back to the ground state. And then this energy, sometimes you can see it if it's something like a fluorescent, right? You can actually see it. Okay. And then the other one is intramolecular rearrangement. Okay, so just an example. So let's say this chemical is very common in the environment. You expose it to radiation, then it can actually rearrange itself to become this molecule, right? So this is very common in the environment. Of course, looking at all this rearrangement of the molecule, how they can actually react with certain things. This is you can assume that this is something that is very commonly occurs in the environment, but in fact it is not, right? It depends on something called the reaction quantum yield. Okay, so this reaction quantum yield means that we actually calculate the ratio between mole of molecule transform, okay, divided by the mole of photons absorbed. Okay, which means we want to look at the efficiency of the reaction to happen. And most of the time in the environment, the organic chemicals that absorb those UV radiation, those infrared radiation, nothing happens. Okay? Most of the time, nothing happens. But of course, sometimes there will be reaction, right? There will be reaction that makes the molecule transform into something else. So all this, we actually have a parameter to know. Okay, what is the probability of this molecule being transformed to something else? So we call it as the reaction quantum yield. Okay, to look into how much the molecule absorbs the photons and how much of this molecule is transformed. Okay, we are looking at the ratio of this, right? So the higher the ratio, the more likely the molecule to be transformed into something else. Or in other words, the higher the ratio, the more molecules is reacted, right? So sometimes you have low quantum yield. Okay, for instance, this reaction, hydrogen plus bromine, the quantum yield is about 0.01. This is very, very low, which means that out of this, let's say this is 0.01, this is 1, and this is 100. So out of 100 exposure to photons, right, only 1 moles of the molecule is transformed. Okay. Whereas for this one, this is about 20%, which means that 20, let's say this is 20, right? Moles of this NH3 being transformed, you have to expose it to 100 of these photons, right? So generally in natural water, right, we can see that reaction can actually happen through the sunlight, because this is the main source, right? Direct sunlight and diffuse sunlight. Okay, we have two different kinds of sunlight. Okay? Direct sunlight is when the sun shines directly to the organic molecule, most of the time triggering reaction, right? Whereas diffuse sunlight mainly is those sunlight that's been shined to the environment, and then it starts to diffuse around, right? So this is less energetic, right? So once the sunlight hits, let's say a certain area, for instance, this lake over here, once it hits this lake water, it will start to have certain effects, right? Number one, it will be surface refraction. Number two will be surface reflection. Okay, that means it can actually go inside to the water, or it can be reflected. Okay, 10-20% will be reflected, right? So once it gets into water, it can actually go to this organic molecules and starts to excite the organic molecules. Okay, which means that these molecules can actually absorb the light, right? So they can also be reflective particles, whereby the light is actually reflected by the reflective particles. So this is how it looks like when you have sunlight in the environment, causing different effects to the molecules, right? So just to show you some of the compounds, like for example, phenatrine, anthracene, these are very commonly found in the environment. Okay, of course it's not nitrobenzene. Nitrobenzene is less likely in the environment. Then we have a TNT, okay, 2,4,6-trinitrotoluene. This is also sometimes found in the environment, when you have a mining area where they use explosive, right? The wavelength, whereby when it is exposed to, you have excitation of electron. This 313, right? Most of the time, you can see that the UV region is the one that can excite the molecules. And usually it excites those aromatic rings of the molecules in the compounds. Okay? All these compounds contains aromatic rings, right? But the reaction quantum mu is very low. Okay? So that means that the reaction in the environment is less likely, okay, very low in terms of the percentage of the photons that they absorb and their reaction in the environment. You can see 1 × 10⁻⁻², which means around 0.02, right? So this nitrobenzene is 0.0003, very, very low. Okay, so that will mean that the molecule is quite stable to photolysis. On the other hand, if you have indirect photolysis, this is what we call as the ability of this light itself to cause the emergence of radicals. Okay, this is indirect photolysis. Direct photolysis is when the light is absorbed by the molecules and it has reaction, whereby indirect photolysis means that when the light itself goes into the system, and then this system starts to generate certain radicals that can actually attack the pollutant itself. Okay, so for this case, if you look at in our environment, we have a lot of these unknown chromophores. These unknown chromophores can actually absorb the lights, right? So sometimes you can have certain reaction of oxygen with the unknown chromophores, and the oxygen can actually be transformed into something called the singlet oxygen. Okay, so this singlet oxygen itself is quite energetic. It is able to continue to attack pollutants, right, or any other organic molecules in the water. Right. So aside from single oxygen, we can also see hydroxyl radicals and also peroxyl radicals in the environment itself. Usually, indirect photolysis is more commonly observed in atmospheric chemistry, right? Especially in the higher areas, whereby ozone layer, right? In our ozone layer, whereby the UV radiation is excessive, right? So that's the part whereby we see a lot of this indirect photolysis and generation of a lot of different kind of radicals, which can cause a lot of harms to the system. Just to share with you, okay, what are the different characteristics of the radicals? You have single oxygen. Okay? Single oxygen, if it's in the water, is not so concerning because it can easily be quenched by water. It will react through certain reaction like Dyer-Alder reaction. This is one of the organic chemistry reaction. And sometimes the concentration of this single oxygen is very low, okay, depending on what are the materials, what are the characteristics of the water, and so on, right? So if you have, let's say, certain materials in the water, like certain carbon materials or certain minerals in the water, it can actually catalyze the production of single oxygen, right? So, but most of the time it is in low concentration, right? And then we have hydroxyl radical. This hydroxyl radical is very, very powerful. It can react with many things, okay? Like DOM. DOM is a dissolved organic matter. This is found naturally. Okay. In our water, we have a lot of these different kind of organic molecules, right? Most of the time, they are from the natural organic molecules, right? So the natural organic molecules consist of many kinds of different chromophores, okay, which can absorb different radiation, right? Then we have peroxyl radicals, and this one have many varieties. It can have like different this R group. Okay, you have CH3, you have ethane group, you have many different kind of alkyl groups, alkene group, many different kind of variety. Okay, and not well scavenged by DOM. Okay, just to show you that this kind of photolysis, right, is actually something that we can use it to our benefit, right? If you look at today's publication and journals, right, there are many people who look into how UV can be utilized to break down a lot of chemicals in the environment. So one particular example of interest would be this study whereby they look into how UV photolysis can lead to the breakdown of antibiotics, right? So in the environment, you have many kind of molecules. For example, these molecules. So when we expose these molecules to UV radiation, it can break down. Okay, for instance, it breaks down in these molecules, smaller molecules. So aside from this AZA, you also have different antibiotics like this CP and so on, right? So from here, right, from the study, you can actually see that UV photolysis is actually quite effective in breaking down certain bonds of the organic molecules, which can lead to something that is less toxic, right? That's why it is quite widely investigated today, okay, by many people. Most of the chemistry of this UV photolysis is already well known, and we also know the disadvantage. Okay, the disadvantage of using UV photolysis would be the difficulty of direct complete mineralization. Okay, so for this UV system, right, very hard for the energy to break down the molecules up to CO2 and H2O level, right? So this is one of the disadvantages. And another disadvantage would be the energy requirement to break down, right? So of course, aside from the disadvantage, the advantage would be it can work very efficiently and it's very simple. So a lot of people are using this technology to actually try to clean Earth, right? Okay, so as you know, right, one of the major problems that we have due to the radicals, right, will be the ozone depletion. I don't know whether you have heard of these issues or not, but many years ago, we actually used CFC in our fridge. Okay, so you use this CFC, chlorofluorocarbon, okay, as one of the ingredients, okay, that promotes cooling in the fridge, and we at that point of time we did not know that CFC is very dangerous, right? We use it excessively, everyone starts to use it, commercialize these chemicals, and it is available in every household in the world, right? So there's no proper life cycle assessment of this chlorofluorocarbon. No one actually knows what this chlorofluorocarbon can cause to the environment. So what happens is that after some time, they start to find that the ozone level decrease in certain parts of the world. So the decrease of this ozone layer, right? You can see, right? This part becomes bluish in color. So the decrease of this ozone layer is something that is not so desirable because it can cause harmful things to human, especially to human. So if you're exposed to this UV, right, without the ozone layer protection, you will have cancer. So this is something that is of concern, and they start to discuss it worldwide. Okay? They come up with a protocol called the Montreal Protocol, right? And they make sure that all countries have to follow these rules. So because of this, then of course CFC was banned. Okay? At that point of time, no more CFC in certain countries. But of course, some countries still use it, but as a lower scale, right? And after a decade or 2 decades, we start to find that the ozone actually recovers, right? And the world actually come together to address this issue, the CFC issue. So this is something that we can be proud of, right? Hopefully the world will come together for the CO2 issue because carbon dioxide is rising, right? So it's causing the temperature to rise rapidly. So hopefully it can happen too. Okay, but this CFC issue is one of the classical example whereby you can see that the world work together to address the CFC issue. So why this is so important? Is because if you look at this chemistry part, right? I included this this reaction. We can see that radicals are being generated, and these radicals are actually the one that cause the ozone to be depleted, right? So in the atmosphere itself, you can see that we have an equilibrium, right? Oxygen can actually be in equilibrium with the ozone, right? So you have this equilibrium, and then if you have CFC in the system, okay, CFC can actually go up to the ozone layer, right? This CFC can be initiated by UV. So this is a photochemical reaction, and then it causes the chlorine radical to be formed. And these chlorine radicals, aside from this, you can also have another radicals, right? These radicals. This is something that can attack your UV and then cause the overall reaction to become oxygen, right? Ozone is transformed to oxygen. So over time, you will see that the reaction will cause oxygen to be increased, but then ozone to be decreased, which is something that is a lot less desirable because ozone is needed to filter off all those UV radiation. Okay, just to show you what kind of reaction pathway that we can have in the abiotic system, in the environment, we can have electrophilic. Okay, so the term electrophilic here means electron lover. Okay, the term philic here means that it likes electron. Okay, so things that likes electron usually they don't have electron themselves, right? So we can say that this kind of electrophilic is mostly positively charged molecules, or maybe partially positively charged because they like electron. They don't have enough, right? Nucleophilic, on the other hand, is nucleus lover, which means that they like to attack the nucleus, which means they have electrons, right? They have electrons and they like to attack those that have no electrons or positively charged species, right? Aside from nucleophilic and electrophilic, we have oxidation, reduction, and other processes that can happen. Nucleophilic and electrophilic reaction happens because there's an imbalance of charge, right? Some may have positively charged structure, while the other, on the other hand, and the other one may have negatively charged structure. So if we talk about in terms of the bond, we have, let's say we have two different atoms. So these two different atoms may have different electronegativity. So when they have different electronegativity, they actually will cause polarization of the charge itself. Okay, one example is shown here. Okay. Let's say you have a molecules containing this chlorine group, right? And you have carbon, okay, bonded to the chlorine. You'll see that because of the high electronegativity of the chlorine, it can actually pull electron to itself. It is a partially negative charge, whereas your carbon itself, having its electron being pulled by the chlorine, will become partially positive, right? So for this case, right, you will see that electrons will like to attack CH2 group because it is partially positive. So usually these are the sites whereby reaction can happen, right? So in the environment, we have many kinds of electrophilic and nucleophilic molecules, right? So majority of it is nucleophiles because they are negatively charged, right? And they like to attack those electrophile. Okay, so if you look at this environmental nucleophile, you have all these groups, sulfate, bromine, this hydroxide, and so on. All these are negatively charged. Okay, nucleophile likes to attack electrophile, okay, because nucleophile, they are negatively charged. They like to go to the positively charged, okay, to balance out. So these are the reasons why we see that reaction always happens due to one nucleophile attacking another electrophile, right? So nucleophile have partial or full negatively charged species, right? And usually when they encounter organic molecules with the polar bond, okay, the electron-rich atom of the nucleophile may form a bond, okay, with the electron depletion atom of the organic molecules, right? So the negatively charged species will attack the positively charged species, right? So usually this kind of reaction is what you call as the SN1 and SN2 reaction, which means that the nucleophile can actually be substituted, okay, into the molecules itself through various approach. Just to look into what are these SN1 and SN2 reaction. SN1 means that it is substitution, nucleophilic and unimolecular, right? So S, N, and 1. Okay, 1 is unimolecular. The way it reacts is that, let's say you have these organic molecules, and you can see that it starts to be weakened, this bond, CX bond. This X here, let's say it's Cl, right? Chlorine. This bond starts to be weakened, and then after that, it forms an intermediate. Okay, this is the rate limiting step. Okay, so once it's formed an intermediate, this X can be released out. Okay, and then it is replaced by Y, okay, in the system, right? It becomes a new molecule. So this is a typical example of SN1 reaction, and this is very commonly observed in the environment whereby you have a lot of halogens, right? You have water containing bromine, bromide, chloride, and also an organic molecules. Usually you will see this kind of reaction happening, right? The other one, on the other hand, we have the SN2 reaction. This one is a bimolecular reaction. Substitution, nucleophilic, and bimolecular. Here you can see that your reaction needs to have two different kind of molecules, okay, or compounds. And then you have the rate limiting step whereby the Y here actually binds with the carbon structure to form this intermediate. Okay, so after that, this X will leave. Okay, this is the leaving group. Okay, you'll leave the molecules, and then you have a new structure, right? So typically SN1 and SN2 reactions very common in the environment. Of course, we still have other reaction like elimination reaction, but that one will be less common. In terms of mechanism, okay, mechanism of hydrolysis, we have a different half-life depending on what kind of structure that you have. If you have something that is stable, okay, this is fairly stable, you'll see that this is 340 days half-life. Okay, and it proceeds through SN2 reaction. Whereas if you have something that with a lot of this large bulky group, you'll see that it proceeds to SN1 reaction. The half-life is about 23 seconds. So other reaction would be alkylation, beta elimination, and chlorination, right? So these are more towards organic chemistry, right? What kind of reaction that can happen when you have different kind of electrophiles and nucleophiles in the environment, right? So oxidation, this is one of the common reaction whereby one molecule is oxidized. Oxidation will mean the loss of electron. Usually is through combination with oxygen, right? So one of the classical example would be apple. Apple is one of the molecules that can be oxidized easily, right? In the environment, right? If you cut an apple and then you put it outside, and you can see that it turns into brownish in color due to the oxidation of certain chemicals. On the other hand, you have the radicals, right? Which can cause oxidation. Like triple oxygen, single oxygen, and so on. All these, they are radicals that they are able to oxidize certain organic molecules in the environment. So reduction is less common in the environment, but it is also can happen, right? Natural reducing agents involve this iron, hydrogen sulfide, iron phosphorine. All these you can find in our red blood cell, right? And then we have sulfhydryl compounds, hydroquinones, and so on, right? So the other one is we have also reductive dechlorination. If you go to the environment, you'll see that we have a lot of different kind of aromatic rings with a lot of Cl group, which is very persistent. Okay, this is one of the pollutants that is very commonly seen in the affected areas. Okay, very persistent, hydrophobic, and it can cause a lot of harm to human, right? So one of the treatment strategies that people employ is through reductive dechlorination, okay? Which means that we subject this kind of pollutant in anaerobic condition, and then this Cl can actually be released, okay, through microorganism action, right? Those microorganisms can actually dechlorinate this kind of molecules, okay? But it has to be under anaerobic condition because this happens to reduction, right? So this is one of the strategies that we can use to remove those compounds that are persistent, chlorinated compounds that cannot be removed easily from our environment. Okay? So we have nitro group reduction also, right? Which needs to happen under anaerobic condition, right? So redox reaction also can happen, but you need to have electron acceptor and donor. So for this case, most of the time, you have two different species which can actually donate electrons to each other. Okay, but then of course, redox reaction depends on the redox potential. If you have a compatible redox potential, then it can happen. So the redox potential itself is actually used, okay, to determine whether this reaction is feasible or not. Okay, so for instance, oxygen, right? This oxygen can actually be converted to H2O, but then the redox this electron E in redox potential is positive 0.81, whereas if you look at this CO2 to become glucose is negative 0.43, right? So positive is usually favorable, whereas negative, it is less favorable. Okay? You need external energy to cause this to happen. For example, CO2 to glucose, you need energy to cause CO2 to become glucose. One of the important things in redox chemistry is this diagram, what we call as a Pullback diagram. Okay, so Pullback diagram is actually a diagram that relates the redox potential with the pH, right? So through this Pullback diagram, we can actually see what kind of phase, okay, what kind of this material phase can exist under different conditions, right? So this Pullback diagram is basically based on the thermodynamics. It is not kinetics. It does not give any information on the kinetics, right? It is only looking into the stability of a specific phase Okay? Just to show you an example, this is an example of a Pullback diagram for lead. So for this case, it looks very complicated, right? So when you look at it, it's very, very complicated in the sense that you have a lot of different species. In the environment, this is what is happening. Okay, in fact, this is not considered as very complicated. This is still okay. There are many different Pullback diagram that is more complicated. Okay, so this Pullback diagram refers to the lead. Okay, lead, carbon, iron, sulfur, and H2O system, right? And just to give you some insights into how we can actually read it, okay, this is actually redox potential, okay, against pH. Okay, and then this redox potential you can see here, 0. Okay, here you have the 0, you have the positive side, you have the negative side. Okay, negative means under no oxygen condition, or in other words, it is under reductive condition, whereas positive means oxidizing condition. Okay, in other words, you can also say that positive means aerobic, negative means anaerobic, right? So this one is pH, okay, pH of the environment. Okay, let's say you have 6, right? pH 6. Okay, you go to a particular area, let's say a lake, you measure that the pH is pH 6, right? And then you take the ORP. Okay, there's this ORP probe, oxidative reductive potential. Okay, you can actually measure it. Okay, if you measure it and the probe tells you that it is 0.2, right? So you can actually see 0.2 and 6. You are at this area. So at this area, you'll see that lead sulfate is the one that is stable under this condition. Okay. On the other hand, if you have pH 3, okay, under 0.2, but it's pH 3, right? The lead sulfide is the one that is stable. Okay. So this diagram can actually tell us which phase is the stable phase. Right? It is actually a thermodynamic representative of the different phase to show us which one is the most likely exist in that particular condition, right? So there are also two things that we have to take note is this part and this part. Okay, there are two lines. Okay, one line is that water is reduced. The other line is that water is oxidized. Okay, so if you are concerned with the water system, okay, let's say you have pH 12 and 0.8, this part, right? If you are concerned with water system, this part is no longer relevant. This dot is no longer relevant for us because it cannot be in the water system because water has been oxidized under this condition. Similarly, if you have, let's say, pH 12 and the ORP is negative 0.8, your water is reduced. So there's no point considering this in your water because water cannot exist at this condition. So this is the same thing, except that it's more complicated, more species involved. And you can see that it is much more complex in the sense that you have more things inside, right? So these are the things that you will see in the environment, okay? Okay, so the next one I want to look into is transport and the fate of the contaminants. Transport and fate means that we want to look into how a particular toxicant in the environment can actually move from one area to another area and what kind of reaction it can participate. Usually a contaminant or toxicant in the environment can be at a local scale, okay, and or global scale. It depends on what kind of pollutant that you have. Okay. Most of the time, if you have a water-based pollutant, it is in the local scale, right? On the other hand, if you have a gas-phase pollution, most of the time, it's very hard to control the gas, the toxic gas. Okay, sometimes it can be in the global scale. For example, if you look at the CFC case, right? So CFC is under this global scale, right? Aside from CFC, of course, we have the carbon dioxide issues. Carbon dioxide has been released continuously every year at an alarming rate. This is also under global scale. Okay? Local is like pollution in your river, like the one in Malaysia. We have a Sungai Kim Kim, which has been polluted by benzene. This is what we consider as local scale. Okay, it doesn't spread to many other rivers in the countries. It's only specific to that particular river. Right? And then we have consideration of the time scale of interest, which means it can be seconds. Right, that particular pollution issues can be like minutes, right? Like in the one in the river, it can be like a few days, right? And then it can also be millennia. For instance, you have radioactive elements, right? It can go up to thousands of years, right? Due to the radioactive pollution. Right? The transport of chemicals have certain effects in terms of its interactions, right, with the molecular events or biological events, right? So if you have chemicals in the environment, it can interact with the different kind of chemicals in the environment. It can be accumulated in the biological system and then it's transported from the biological system to some other places, right? And there's one thing called the chemodynamics, right, which studies all these things: fugacity, volatilization, dissolution. Transport of chemicals have very important interactions between the chemodynamics and the forces of nature, which means that those forces of nature can actually transport these pollutants, okay, from one point to another point. Okay, so very important in terms of the transport, because if you have a pollutant in a localized area, it's transported somewhere else, the pollution problem will go to somewhere else, which is why we actually have to control it at the point of where the pollution starts to happen, right? And in terms of investigation of the pollution issue, we have this mass balance. Usually we use mass balance to calculate what's the percentage of this pollutant is volatilized, what is the percentage is degraded, and so on. Right, so just to show you, okay, an example of pesticides. So if you have a pesticides in the environment, right, these pesticides when applied to this plant, right, for instance, right, you have a lot of these pesticides here for agricultural purpose. For example, these pesticides can undergo many kind of fate. Okay, it can be transported through wind erosion, okay, which means that it can actually go from one point to another point. It can be washed off, okay, which means that it is washed by the rain, okay, going into other places. It can be airborne, which means volatilized. Okay, all those can become like gaseous species. Some of your pesticides can be absorbed by the soil. Okay, it can undergo chemical degradation. This will be our focus later. It can leach into the groundwater, okay, causing harm to the groundwater and drinking water. And in fact, it can also be photodegraded, okay, through the abiotic reaction that we talked about just now, right? So these are some of the examples of the pesticide fates that can happen. So this is something that is quite realistic, and it's happening in terms of the pollutant is actually being transported from one point to other points, right? One example would be this usage and loss of pesticides in China in 2011, whereby we can actually look into this mass balance, right? So the mass balance study has been conducted by them, and then you can see different areas they apply different pesticides, right? Like for example, paddy grain land, they applied 52.4 million kilogram, right, of these pesticides. Okay? So after conducting mass balance, what they found was that about 7.78 million kilogram of these pesticides has been lost due to many different reactions, Okay, so for of course the uninformed people, they look at this 7.78 million kilogram loss, they'll be of course very concerned, right? Because they will say that these chemicals is in the environment, it is causing harm. But this, most of the time, this is not the case, because today most of the pesticides, they're designed to be biodegradable. They're designed to be easily decomposed in the environment. So we as a chemist, right, we know that this 7.78 is actually not in its original structure. Okay, so this 7.78 can be undergoing photolysis, it can undergo degradation, it can undergo many different kind of reactions in the environment, and it can be lost due to its degradation. Okay, so but then of course it is also concerning, because some of these countries, some of the countries may use certain pesticides that can be very stable. For example, look at the example last week, we talked about the glyphosate. Some of these chemicals they are actually quite stable when they bind with certain heavy metals, right? So this is something that we have to take note of, right? Chemical reaction, okay, in the environment, we can have many different kind of reactions, right? So this is our interest today, because we as a chemist really look into how chemical reaction can aid in terms of the fate and the transport of the chemicals, right? So inorganic chemicals here refers to things like heavy metals, right? It can undergo many kind of processes like solubility, dissolution, precipitation, complexation, absorption, ion exchange, redox chemistry. On the other hand, organic chemical, you can undergo absorption, hydrolysis, ionization, volatilization, dissolution, and in fact, even degradation, right? So we want to explore one by one, look into what kind of process, what kind of fate can happen to the this pollutant in the environment, right? First will be the absorption. If you look at the environment, we have a lot of different absorbents. Okay? All those natural materials like clay, we have carbon structure in the water. Sometimes you have different kind of minerals, right? So all these, they are capable of acting as adsorbent, right? So when you have a pollutant, right? Pollutant like organic contaminants, sometimes you have heavy metals. This kind of pollutant can be attached to a adsorbent. Okay, so this is just an example of a process. You have sorbent here, right? This one can be clay, can be activated carbon, can be anything that has a surface, right? This surface consists of functional groups. For instance, this one contains carbon bonded with these oxygen groups, right? This is like a carboxylic acid group, right? So the sorbent can have like different functional groups, like maybe like carbon group. You can have carbon with a OH group, right? So this kind of functional can actually act as active sites for adsorption to happen, right? For instance, if you look at the copper here, right, it can be attached to the oxygen group. Whereas if you have organic molecules, right, this organic molecule can also be attached to this group, okay, these functional groups. So different classes of molecules can attach to the adsorbent through different mechanism. So for heavy metals, usually we have something called a electrostatic interaction. Whereas if you look at organic molecules, usually you have something called a pi-pi interaction. Okay, so all this interaction will cause that molecules to be stick to the adsorbent. In other words, we call this an adsorption process. Right. So aside from adsorption, sometimes your pollutant can undergo hydrolysis. This is commonly occurring to these organic molecules. Hydrolysis means that your molecules can actually be hydrolyzed or reacted, okay, to become smaller species. So hydro here, right? The term hydro here means that it is water. Okay, lysis means that it is decomposition. Okay, that means it's the breakdown, right? So hydrolysis can happen in mostly organic molecules like ester, right? So your ester can actually be hydrolyzed by water to produce carboxylic acid and also alcohol. This is just some example of hydrolysis reaction. Then we have co-solvation and ionization reaction, okay, which can happen in during the transport, okay, of the chemicals from one point to another point. So co-solvation basically means that you have one chemicals, maybe it's not so soluble, it's very hydrophobic, but because of the presence of another pollutant, such as methanol, right, in the water, it can actually increase the solubility of that pollutant, okay, the first pollutant, and it can be transported. Okay? It can increase the transport of that particular pollutant, right? So just to illustrate it to you, if let's say you have in the water you have these hydrophobic molecules like benzene, right? Then you also have methanol, right? So this methanol increase the solubility of this benzene in the water and cause this benzene to be able to be transported via water from one point to another point. This is what we call as a co-solvation, right? Another one, it would be the ionization, let's say benzene ring. You have this phenol. This is phenol, right? You have OH group here, right? It can actually be ionized to become oxygen with a negatively charged. So this negatively charged oxygen is more soluble compared to the one that has no negative charge. Okay, so this is what we call as a molecular form, right? So the molecular form solubility is lower compared to the ionic form. So if you have ionization, then you can actually increase the solubility of a particular species, causing it to be more soluble in the water and causing it to be able to be transported more efficiently. Right? Then we have this volatilization and dissolution, which means that your pollutant can actually be volatile, right? Such as this NH3 here. So NH3 is one of the pollutant, but it is also a nutrient, right? So if you look at the NH3, right, it's actually in equilibrium, NH4 plus and NH3, right? So NH3 itself can be volatilized out from the soil, right? If you have a NH3 in the soil, and if the pH of the soil is basic, okay, pH 7, pH 8, right, it can actually be liberated out as the gas itself, and then it's transported from one point to another point. For inorganic chemicals, right, like heavy metals, okay, especially heavy metals, it is very, very concerning, not because of its total concentration, but it is more on the speciation itself. Speciation here means that what kind of species that particular metal can exist, right? For instance, it can exist as a free ions. It can be insoluble species. It can be a complex. Okay? Complex formation is quite important because complex itself is something that can have a different characteristics compared to the original compound, right? So the species can also be the adsorbed species, immobilized species, or maybe a species that have different oxidation state, like arsenic, right? Arsenic 3+ is more toxic than arsenic 5, right? So this is the things that we have to be concerned of in terms of the species itself for heavy metals, and not the concentration, because the concentration is quite meaningless to know it, right? This is the Pullback diagram that I shared just now. Okay, this is in terms of the iron itself. Okay, you can see that using this diagram, we can actually predict what kind of species that exist, and different species have different toxicity, and different toxicity will have different effects to the system, right? So you have reducing condition, you have Fe2+. Under oxidizing condition, you have Fe3+, right? So these are the different species that can exist in water, right? Depending on what kind of environment you have. So heavy metal can cause many toxicity, different oxidation state, different biochemical processes. Right? For instance, mercury can cause inhibition of protein synthesis. And cadmium can cause a respiration problem, photosynthesis problem, transpiration problem, depending on its oxygen state and what kind of species it is, right? Because different species means different bioavailability, right? Different bioavailability means that different absorption and different endpoints. So in terms of solubility, of course, some minerals can have a different solubility in the so-called system, right? If you have a lot of minerals, then of course you will have more dissolution, right? So all these will actually harm the environment in the sense that they can actually modify pH. They can actually cause the leaching of different kind of heavy metals and so on, right? One of the most important things, right, important reaction in the environment will be the complexation reaction, which is the reaction of metals with your ligand, right, to form a complex, right? So complexation itself is concerning because if you have complexation of heavy metals, you can change the characteristics of the heavy metals, right? So initially the heavy metals may not be toxic, but once you complex it with something, it can be more toxic. Complexation can also affect the transport of the chemicals itself, right, or the heavy metals itself. So sometimes if you have a complexation reaction happening, you can actually increase the solubility of that particular heavy metals. Just to give you an example of how complexation can increase the solubility, we look at this example. We have this chemical, nitrotriacetic acid, or we call it as an NTA, right? So this NTA itself is chemicals that can complex with lead. Okay, so in terms of the ability of the complexation, the strength, right? Different heavy metals have different strength, right? You have Fe3 is more than Cu, is more than nickel, is more than cadmium, and so on. So this NTA can complex with everything, but it depends on what kind of heavy metals you have. And the ability of complexation depends on the heavy metals characteristics, okay? The affinity of reactions. And as I said just now, it can increase the solubility of lead in water. Okay, it has a tendency to complex with lead at a significant rate. Okay, so the Ka value of this complexation is very high. Let's look at an example of how we can actually increase the solubility of the lead hydroxide. So this lead hydroxide is actually a solid. Okay, it is a precipitate. Okay, so there's an equilibrium between this lead hydroxide in the water. So this lead hydroxide can actually be forming lead 2+ and this OH group. Okay, so the KSP value is 1.61 times 10 power -20. So KSP is the solubility product constant. The higher the KSP, the more soluble it is. Right? So once you reach the KSP value, that means you will start to see precipitation happening. Right? So for this case, you have lead hydroxide, okay, and then you have this HT is the chemical that I showed you just now, triacetic acid. This one, nitrilotriacetic acid. Okay, it is also able to dissociate in the water depending on the pH and the Ka value. So there's an equilibrium between this Pb2+ and this T3+, 3-, right? So you can actually have this reaction also, right? The lead can actually bind with the ligand to form a complex, right? So first reaction is when you have dissociation of the lead to become the ionic form, right? And then second reaction, you have this dissociation of this Ht2- to become H+ and T3-, right? So this is the dissociation of the organic molecules, which depends on the Ka value, whereas the dissolution depends on the KSP value. And then aside from these two, okay, if let's say this Ht2 minus is not present because we only have the first one. But if the second reaction is also happening, then we will have a third reaction, which means that the lead here, this one, can actually bind with your T3 minus here to form a complex, right? So this is concerning because if you calculate based on the KSP value and the Ka value, you can actually find out that the ratio between PBT minus, this is a complex, and the HT2 minus, right, is 20.7. That means in the water itself, if you have this excessive HT2 minus, you will see that most of this will actually exist as lead complex, right? So you can actually increase the solubility of the lead in the water through this means. Aside from increasing the solubility of the lead, you can also, complexation can also change the characteristics of the heavy metals, right? So for this case, if you look at the copper, right? Copper binding with NTA. Okay? Initially, if you have copper itself, it is toxic, but after binding with NTA, it becomes less toxic, right? So this is a case whereby toxicity can decrease with complexation. You can also have cases whereby toxicity increase with complexation. So there are two ways. Okay? Complexation can increase the toxicity or decrease the toxicity, depending on what ligands you're looking at. So because of this change in characteristics, sometimes we observe certain problem if we want to remove heavy metals from water. So there are many chemicals used to remove heavy metals from water, like for example, ferrous sulfate, DTC, sodium sulfide, and so on. So because of the change in characteristics during this transport of the chemicals, like for example, the glyphosate example that I gave you last week, glyphosate can bind with heavy metals. Glyphosate is a pesticide, right? So after binding with heavy metals, it goes to wastewater treatment plant, and the wastewater treatment plant use all these chemicals to remove it, but it's no longer effective because the characteristics of the heavy metals has changed drastically due to the complexation reaction, right? So aside from complexation, we have ion exchange. So ion exchange is when you have the ions in the clay being exchanged with the pollutant. One example is this one. You have A, B, C, D. Then after ion exchange reaction, your B is changed with the D, right? You have AD and BC. This is one of the example whereby you have anion binding with the clay. So naturally, you have a lot of clays in the environment, like kaolinite, kaolin. All these are example of the clay, right? So all this clay may have heavy metals. So when you have ion exchange reaction, you can actually release heavy metals into the water. Sometimes the clay don't have heavy metals, but in the water you have heavy metals. In that case, you can actually have ion exchange reaction that absorbs all the heavy metals, right? So it works both ways. You can have heavy metals being released and absorbed by the ion exchange. And then the one thing that is important in the transport is the redox chemistry, and the oxidation state itself is quite crucial because it can actually determine whether it's mobile or less mobile. If it is chromium-6, it is toxic and mobile, whereby if it is chromium-3, it is less toxic and it is immobile, right? So it depends on the oxidation state in terms of the toxicity of the heavy metals, right? Okay, just to highlight some of the factors that affects the mobility in water, we have amount and form of the metals, right? For instance, if it's solid phase, it's precipitate, then it's very difficult to be mobile. It is just localized. If it's sometimes soil properties affects the metal retention, right? You have the soil organic matters, one of the primary immobilizing processes. Sometimes you have adsorption, sometimes you have reaction like a formation of ligand, complex through ligand reaction. Just to show you how this metal can be in the environment, you can see that let's say we are looking at this Fe, it can actually undergo many kind of processes like complexation, you can have oxidation, reduction, precipitation, and so on in the environment. It's very, very complex, right? So the transport and fate of the chemicals in the environment is very complex, which is why sometimes when we want to produce certain chemicals and commercialize it, we have to look into the life cycle assessment to assess what can happen to these chemicals if it's in the environment. Okay, what is the end point? What is the end of the life cycle of that particular chemicals? Right. So we don't want the chemicals that, for instance, like chlorofluorocarbon, whereby its end point or the end of life cycle will be at the atmosphere, whereby it causes ozone damage. We want it to be become something that is less toxic. For instance, let's say we introduce chemicals, we want it to be degraded in the environment, and that is the target end of life cycle that we want. Okay, just before conclude, just to go through this the atmospheric transport. So atmospheric transport is something that is of concern because something that is airborne is more difficult to remove, and sometimes it can cause higher impact, right? So things that are in the air is something that is easier to be transported from one point to another point. One example would be acid rain, right? So acid rain is due to NO2 and SO2, right? So this nitrogen dioxide and sulfur dioxide, if it goes to the atmosphere, it can actually react to form sulfuric acid, nitric acid, which can come back to us in the form of sulfuric acid and nitric acid, right? Or what we call as acid rain. So this acid rain is a typical example of atmospheric transport that has a significant concern because acid rain can cause corrosion, it can cause change in pH of the water, it can cause harm to the aquatic life, and even it can damage buildings, right? So this is why we have to make sure that we don't cause significant toxic acid rain in our environment, right? So I think that's all that I wanted to share today. Thank you so much for listening. Yeah, I'm happy to take questions.
All right. Thank you very much, Dr. Wenda. Very interesting, yeah, especially on elaborations of the variety of the abiotic reactions in the environment. Yeah, you provide us the great examples, starting from the photochemical reactions. Yeah, and the basic principles, how the light interacts with the chemicals, with the material, and also some impact that can be occur, and also some good example from the abiotic reaction pathway. Yeah, very detailed, many type of transformations as well as the chemical reactions that can be occur during the transport of the chemicals in the environment. So for the students, if you have any question, Dr. Wenda will be very happy to take your question, please. You can open your microphone, or even you can do as well in the chat box. Yeah, just send the questions. So Dr. Wenda, in general, if I how to say, follow your lectures, we already known many series of the, how to say, a pathway or how to say, reactions that can be occur in the environment, but it should be depend on the type and characteristic of the chemical, right? What kind of the reaction that can be occur in something?
Yes, it depends very much on the characteristics of the chemicals. Whether the chemicals can react or not depends on the functional group. Let's say if it's organic chemicals, it depends on the functional groups of the chemicals. It depends on how the chemicals can react as electrophile or nucleophile. Yeah, in the environment, you know that we have a lot of different kind of chemicals, right? So sometimes these chemicals can trigger the production of radicals, right? Like hydroxyl radicals, like singular oxygen, and all these radicals can in turn attack more organic chemicals. Because when we talk about this sunlight, like UV radiation, right? It is actually a high energy radiation, which the energy has to go somewhere, right? So if we have organic molecules, of course, this energy will go to the organic molecules, and then it will cause certain effects to the electrons, like I mentioned just now, from the ground state to the excited state. And then when it is at the excited state, then this molecules is energized. It can react with anything. It can also have indirect photolysis, whereby it can be degraded to become radicals, right? So that's the thing. It's very difficult for us to study what kind of radicals is generated and how it is happening in the environment, right? It's because in the environment there are thousands of chemicals, right? If you go to the, let's say we want to look into a river, right? We'll study the river water. We go to the river, we collect samples there, and then we analyze for the chemicals that is in that water itself. You will see that there are thousands of chemicals, right? And it's very expensive to do so. Right? In Malaysia, if I want to analyze for antibiotics, right? I collect the water and then I send it to the lab. Let's say a commercial lab. They charge a few thousand ringgit just for one sample, right? So it is very expensive to do this kind of study to really determine the fate of the chemicals in the environment and how it is actually interacting with each other. The real life, the real water, very, very expensive to do so. And the other one is that the radicals that is generated due to this photolysis reaction, they are very short-lived. So they generate and then they are gone, less than 1 second. So quite hard to do that study. So that's why most of the time when we want to do this kind of study, we will just do it in the lab under controlled condition and look into how they can actually react with each other. But we know, okay, from our organic chemistry experience, we know that if we have nucleophile, electrophile in the environment, and when they are present, they can actually react. Okay? Yeah. So we have many different kind of reaction.
And also maybe the environmental parameters, or conditions could be also another factor.
I think I have several slides last week that shows that these chemicals, some of the parameters, they are quite important. Whether the chemicals can be undergoing photolysis, we look at the half-life, and then we do at hydrolysis, half-life, all this. Yeah, these are quite important. And in terms of predicting whether chemicals can react or not, we can use computational methods to look into that. Right, that one will be a much cheaper way to look into it. Yeah. So.
All right. Yeah. So not the simple system. Yeah. It would
be
more
it is very complicated.
Yeah. If you present it. All right. So the student, do you have any question? Please, Sipa. No. Yeah. And regarding to the speciation, I guess this also quite typical, can be occur in the environment.
Yes, actually, speciation study of heavy metals is quite well established, and it is a very big topic by itself, right? Of course, I don't have enough time to share how we can actually look into speciation of the heavy metals, because this is also not part of the syllabus, right? But just to share with you, it is quite comprehensive, and metal, especially metals, right? It can exist in many different forms, right? Before this, we actually did some speciation study in my country, in Malaysia. We went to river, right? We go to river and then we actually collect the soils, right? The sands, and then we take this sand, we do certain treatment to find out what kind of species that particular heavy metal is. So from this is actually quite established in the sense that for, let's say, for copper, we know what kind of copper can exist, right? But then of course, knowing this is not enough. Like, we have to come up with certain treatment, certain remediation steps to ensure that the species itself will not cause harm to that particular area. But what I can say is that speciation is something that is very complex. The one that I showed you just now is the lead, right? If you look at the lead, let me just go back to that. Just to go through this quickly. Okay. This one. Yeah, this one is, you look at it, is very, very complicated, and the first look then is very hard to understand. But just to share with you, all these lines, right, you can actually calculate it based on the electrode potential. You can calculate it based on the concentration in water and so on. This is what I teach my students in environmental chemistry course. How we can actually, but we don't look at this complicated diagram. We look at the more simpler one, which is the iron one. So this one, this one, I don't know whether you have this in your environmental chemistry course or not.
We introduce.
Oh, you introduced. So we can actually calculate all these lines, and then we have the basis on how to calculate it based on the equilibrium constant. We have the concentration of the maximum concentration of iron in the water and so on. So we derive all this line, and then we can actually look into what kind of species exist at different condition, right? So this is actually a very useful diagram. I have a graduate book full of this kind of diagram, which of course I can ask the students if they want.
For each type of metals,
Yes, for different kind. All metals have their own diagram.
Different pattern. And in case of the metal ions, we also can, how to say, find the phenomenon that we call like the methylation. For example, like mercury become methyl mercury or other.
Yes.
And it would be correspond to the different toxicity, right?
Yes, that's right. So methyl mercury will be I would say it can bioaccumulate because it can be soluble in our fats. So because of this, right, then the methyl mercury becomes more toxic because it can bioaccumulate. Right, so that's one example. So we have many different species. But
it depends. Alkylation must be, how to say, predominantly occur by how to say, microorganism activities or something.
Yes, that's right.
The transformation.
Usually formation of methyl mercury, I see it in this under anaerobic condition with microorganism. So you also need light. Sometimes you also need. You can also do it with photo methylation, but without light, it can also happen through microorganism. Under anaerobic condition, right? So if you look at this diagram, right, this is for iron and oxygen. This is just mainly, you can say that this is just for iron only. So if you want to add in like things like, let's say we are using Hg, right, mercury, you can actually add in the metal, like for example Hg, and then you have Me as one of the species, right? So the whole thing will be very, very complicated. You will see that you have many different kind of species that exist, right? Sometimes you have more than one species that can exist at a particular condition, so you have to add in that species too. So the whole thing will become like, maybe you have one region here, one region here, all this very small region makes things very, very difficult to interpret.
And also when the alkyl groups different, for example, methyl, ethyl, and so on.
Methyl is less toxic, but if you have ethyl, if you have increasing
alkyl
chain length, right, it becomes more and more toxic for mercury. So for that case, right, but now of course we are lucky because only methyl mercury is the one that is more stable compared to the others.
All right. Thank you, Dr. Wenda, for the additional explanation. So to the students, you still have any questions? And I do hope that you can follow the instructions for the second assignment, Dr. Wenda?
So second assignment will be the presentation, right? So the due will be in 2 weeks time, right? So hoping that I can get some very good videos from the students, because now the younger generation, right, they like to do all this video editing, and so I can see that the videos that produce is very nice. Like last time, I remember last time on water treatment, right? We also did a video.
Yes, yes,
Yeah, the
yes.
students did quite very well presentation, you know. I enjoy watching all the videos.
All right.
Mm.
And the second assignment will be in the group or individual assignment?
The next one will be the third one, right? The first
Oh,
one will
I
be the first one we did it already in terms of the questions. The second one is the presentation. The third one will be questions. It will be individual, right? And it will be tougher questions. Something that can spark our thinking.
All right. All right. Yeah, thank you, Dr. Wenda, for the guidance. So since we are left of time, I guess we can close for today lecture, Dr. Wenda. Thank you very much
You
for
so much.
your great lecture for today. And to all students, I will post the teaching materials in our learning management system, as well as you can personally, how to say, access from the link that provided by Dr. Wenda. So I do hope we can see you again next week. We still have a couple lectures to be completed with Dr. Wenda. And very a great day and also great weekend to all of you, especially for Dr. Wenda. Thank you very much again.
Thank you.
Dr. Wenda.
Thank you.
Okay, see you.
See you.
See you then. Baik, semuanya ini perkuliahan sudah selesai. Saya kira bisa di stop ya recordingnya.